In this video, we're going to look at an example of computing vector projections. So we're given the vectors A, which is -2, 3, -6, and B, which is 5, -1, 4. And we want to compute the scalar and the vector projections of B onto A. So we're just going to apply our formulas that we've already developed for vector scalar projection and vector projection. So remember, the component of B along A, which is our scalar projection, is defined as the dot product of A and B over the magnitude of A. And remember that this value gives you basically how far in the A direction does B go. Okay, so if you look at the picture, A is this vector that's along this red line, and we're going to project the vector B, which is this vector here, not on that line, onto A. So when I say that the component is how far in the A direction does B go, we're looking at how much of A is in this direction. How much of B is in this direction along where A is pointing. Notice it's going to be negative in this case because the projection is going against the direction that A is in. All right, so we compute the dot product. So we have the 5 times the -2, the -1 times the 3, the 4 times the -6, doing the dot product of A and B. Notice that I've actually done that in the order B to A, right? I've really done B dot A, but we know that the dot product is commutative, so there's no issue with that. The magnitude of A is just the square root of -2 squared plus 3 squared plus -6 squared. Simplifying, we get -37 over 7. All right, so now we can calculate the projection. We can do that in a couple of different ways. We know that the projection is the component of B along A, and then times the unit vector in the direction of A. So we make a unit vector and then multiply by the amount of the how far in the A direction B goes, essentially, is what I mentioned before. We can do it that way, or we can just use our formula for vector projection, which is A dot B over A dot A times A. We actually get a vector here. So we computed A dot B in the previous part. That was 37. -37, pardon me. We also computed A dot A in the previous part because A dot A would be the denominator here without the square root, so that must be 49. So we get -37 over 49 times the vector A, and we can distribute that through to get our final vector of 7 over 49, -111 over 49, and 222 over 49 as the three components. And again, here we can see the vector, the projection vector here. Here's vector B. We go perpendicular to the line that would contain A, using A as a direction vector there. Go perpendicular, and then this green vector is what's representing the projection of B along A. And then the magnitude of that vector would be this -37 over 7.